So thanks very much, and I appreciate the invitation to address this conference. LSST, or the Large Synoptic Survey Telescope, is a fairly high-profile astronomical facility, also involved with fundamental physics measurements. It's received a lot of attention. I usually give talks about this project to astronomy and physics audiences, where I emphasize the science. It's nice to talk at an optical engineering conference to talk a little bit about the technology. It's interesting to give this talk coming after the last one because this is definitely a one-off project. Almost every element of this project is making a single unit, which is pushing the state of the art. And of course, that has driven the costs up, so it's not a particularly cheap project. So let me start just by telling you what LSST is and why is it different from all other telescopes. The idea here is to build an integrated survey system that will cover the entire southern hemisphere of sky, and to do that repeatedly over 10 years. So roughly in 10 years, we obtained something like 800 to 1,000 observations of every part of the southern sky. Believe it or not, although we've been building telescopes for hundreds of years, we've actually surveyed only relatively small parts of the sky, particularly if one goes fairly deep. The essence of LSST is to go deep, wide, and fast. That is, to get to fairly faint magnitudes, faint objects in the sky, to do that over a large part of the sky at any given time, so we can cover the whole southern hemisphere in a reasonable amount of time, and then to do it fast, obviously, so we can get all these many visits. So over the 10 years, we'll measure everything that moves in the sky by comparing different images taken at different times of the same part of the sky. We'll measure everything that varies in brightness over the sky, variable stars, explosive objects. And if we add together those 800 to 1,000 images, we'll measure everything in the sky. And LSST is actually pushing the state of the art. It will get down to a level where effectively you run out of galaxies that you can resolve from the ground. So it is, in some sense, the ultimate optical survey experiment that you would build on the ground. So over the decade of observations, we'll acquire, process, and make available something like 5 million images. Those images will contain about 37 billion objects, about 20 billion galaxies, and 17 billion stars. 20 billion galaxies is an interesting number. That's something like 10 to 20% of all the galaxies in the observable universe. The observable universe is finite because as you look further out into space, you're looking further back in time, and eventually you get to a time where there weren't any galaxies. So for the first time, we'll catalog a much larger number of astronomical objects than there are people on Earth. Everybody on the Earth can own a few galaxies and a few stars, and look at that. And so the possibilities for the science that will come from this extensive survey of the universe are really impressive. 37 billion objects and 7 trillion sources. We call a source something that was there at some point in the sky at some point in time. And by measuring everything that varies, we will issue alerts, what we call time domain events. Something has changed in that part of the sky. And over the 10 years, we'll issue tens of billions of time domain alerts. As I'll cover later, we'll do that within 60 seconds of having obtained the exposure. So each night, there'll be something like 10 million time domain alerts issued. Astronomers are used to what they call target of opportunity observations, of getting notified that something has happened in the sky so they can follow it up with another telescope. It's going to be hard to do that when there are 10 million per night. So one of the interesting challenges there is to figure out how to filter on that sample to find the really interesting things. So as you can imagine, when you have this kind of capability, you actually enable a very wide variety of distinct scientific investigations, all utilizing a common database and alert stream. And I'll cover a little bit of this more. These range from searches for small moving bodies in the solar system, measuring things that move, to precision astrometry of the outer regions of the galaxy, measuring slight motions of stars as the Earth moves around the sun in its orbit, to systematic monitoring for transient phenomena in the universe. And LSST will also, and this is where the interests of the physics community come in, provide crucial constraints on our understanding of the nature of dark energy and dark matter in the universe, which are two of the greatest mysteries actually facing fundamental physics at this point in time. So the project has a long history. The idea for it started in the 1990s. Some of you may be aware that the astronomy community undertakes what are called decadal surveys every 10 years, where the community gets together, hears about ideas for different projects, especially big projects, ranks them, and then with that ranking, the funding agencies can move forward. And LSST was the highest ranked project, ground-based project, in the 2010 decadal survey, which the cover of which is shown here. It was called New Worlds, New Horizons. And those of us who were working on this project were particularly proud not only of getting the top ranking, but the reason we were given the top rank was that the project was considered technically ready. And for a far-ranging project like this, that's a real testament to the many engineers and scientists who were working on it, that they'd matured the design to a point where the funding agencies felt they could move forward. So this is a complex programmatic project as well. It's a public-private interagency project. The lead agency is the National Science Foundation, which is funding the development of the telescope and the site, as well as the data system. This is what's done, it's called a Major Research and Equipment and Facility Construction Project, an MREFC project. And we were approved with a total not to exceed cost of $473 million from the NSF. And the lead contractor for that work is the Association of Universities for Research in Astronomy, AURA, through a cooperative agreement. AURA is the organization that runs a number of other of the large national observatories. The minor federal agency partner is the Department of Energy. They are supporting the fabrication of the camera. And this is being done as a major item of equipment through the Office of High Energy Physics with a total projected cost of $168 million. And the lead laboratory for that work is SLAC National Accelerator Laboratory at Stanford, which is overseeing the camera development. And then we could not have gotten this federal money if we hadn't also actually collected a fair amount of private money. In particular, we solicited about $40 million. And this was crucial because it enabled us to start the long lead procurements, which got this project off the ground. If you have to wait for federal approval, then you can't actually fabricate anything until you have all the money, and it's sort of hard to make progress, particularly on long lead items. So the private money enabled the fabrication of the primary tertiary mirror, which I'll show you, acquisition of the secondary mirror blank, some of the site preparation, and some of the early sensor studies. And the responsible organization for that was another nonprofit, what we call the Large Synoptic Survey Telescope Corporation. So, as I mentioned earlier, the science from a capability like this is extremely broad. But we defined 4 science themes that allowed us to flow down the science requirements. And those were taking a census of moving objects in the solar system, mapping the structure and evolution of the Milky Way, exploring the transient optical sky, and determining the nature of dark matter and dark energy. And the reason we chose these 4 is not because those are necessarily the most important scientific investigations you could carry out with LSST, but they stress the system in very different ways. And so by satisfying the needs of those 4 science disciplines, we could convince ourselves that we would develop a truly broad-based capability. So for example, the studying the moving objects in the solar system relies on precision astrometry, a very precise determination of where a given object is at any given time, as well as the ability to track that movement and connect different sightings into orbits. Mapping the structure and evolution of the Milky Way, again, requires precision astrometry, the registering of different fields taken at different times. The transient optical sky requires us to process the images very quickly and issue these alerts that I spoke about earlier. And determining the nature of dark energy and dark matter, one of the principal techniques for doing that is by measuring something called weak gravitational lensing, which is a very subtle effect, a correlation in the shapes of galaxies that are nearby in the sky. And that requires very, very good knowledge and control of the point spread function of the system. So putting all those together gave us a truly broad capability, and we captured those requirements in the science requirements document, which was written in 2011, and I'm proud to say has not changed. It's not uncommon with these big projects that you sacrifice some of the science as you go along and face real world problems. We haven't had to do that yet for LSST. So for the astronomers in the audience, this is a sort of summary of what the high-level requirements are. We'll cover about 18,000 square degrees of sky. Each part of that sky will be covered a minimum of 825, that is 825 separate visits on that part of the sky. A single visit corresponds to a pair of two 15-second exposures separated by a 4-second readout. We'll do this in 6 different colors, 6 filters, what are called UGRIZY, which cover the entire optical band from 320 nanometers out to beyond a micron. The single visit limiting magnitudes indicate how faint we'll go. We'll go to about 24th magnitude in one pair of 15-second exposures. And over the 10 years, we'll get down to something like 27th magnitude, which for those of you who've seen the Hubble Deep Field images where you basically see a forest of galaxies, we get down to those limits in a ground-based project. A lot of the science that will come from LSST requires precision photometric calibration, so we have to be able to compare exposures taken at different times and taken in different color bands, and we require ourselves to do that with 0.5% repeatability. That's tough. Traditional experiments have only gotten down to about 2% repeatability, so we put a lot of effort into photometric calibration. We're building this telescope at a good site where the median seeing at the site is about 0.6 arc seconds, but we put a tight constraint on the rest of the optical system that the total median delivered image quality is only 0.7 arc seconds. So there's not a lot of freedom for the mirror quality, the camera quality, et cetera. And then one of the interesting constraints is this transient processing latency. So within 60 seconds of closing the shutter on the telescope, which will be in Chile, I'll come to that later, we have to transfer all of that data to our processing facility in Illinois, reduce the image, compare that image to a reference image, determine everything that's varied, and broadcast that to the world. So 60 seconds for that entire time. That puts lots of constraints on the data system and the speed at which we can process the data. And then every year we'll process all of the data we've taken up to that point and release those results annually. This just gives you an idea of where this project is. So this is a picture that was taken just last month in Chile, and you can see the large facility itself, which is the main building. I'll show you some blow-ups of this later. And there's actually a separate telescope, which is part of this, which is a calibration telescope that will do spectroscopy simultaneously with the imaging to measure the transparency of the atmosphere. And that turned out to be crucial to get to that 0.5% photometric precision that we talked about earlier. This is where the schedule is. There are 3 main development arms of LSST: the data management arm, the telescope and site, and the camera. This is where we are now. So you can see we've been working on this for a number of years. We got formal approval in 2014. Things are starting to come together. We will begin to commission the system in late 2019, beginning of 2020, put the whole thing together, and then we're scheduled to start operations in October of 2022. So let me now turn to the technical design. So LSST is challenging because we need the figure of merit for a survey telescope is what we call the étendue, the product of the collecting area of the primary mirror times the field of view of the camera. So high étendue allows you to go deep and to capture a lot of the sky in any given exposure. And then obviously the field of view determines how many exposures you need to cover the southern hemisphere. So the requirements on LSST is that we have a large aberration-free field. In fact, the field of view for LSST is 9.6 square degrees. It's about 40 times the size of the full moon in the sky. And we have to step this thing around very rapidly. So we need a very fast optical system. LSST is f1.2. If we had a slower system, which was longer, the time that it would take for the telescope to settle after slewing it would be considerably longer. So the design incorporates an 8.4 meter primary, we call M1, a 3.5 meter secondary, and a 5 meter tertiary, M3. So the tertiary on LSST is the size of Palomar, for those of you familiar with optical telescopes. Now, as you can see in this ray diagram, this is M1, and this other surface is M3, and they're nearly coplanar, which allowed us to consider making both of those optics out of the same monolithic substrate. That was a challenging thing to do. I'll show you a picture in a minute, but it greatly simplified the integration and the control of the facility later. There were also 3 refractive optics in the camera, which we call L1, L2, and L3. There's not a lot of power in those optics. They mainly are there to eliminate chromatic aberrations that would otherwise be introduced by the entrance window to the door. And then there's an optical filter, which defines the color bands, which is actually a curved substrate with an interference coating on it. All of the optics, all of the mirrors, and the 6 degrees of freedom for the camera are actively controlled. And so this is to enable, we measure the wavefronts real time and to enable the fine tuning of the system to maintain that very tight image quality spec. The design has also been optimized to reduce asphericity in the various elements and to ease in testings. And actually one of the architects of the optical design for LSST is Lynn Seppala from Livermore, who's actually in the audience here, sitting in the middle of the room. So I mentioned that M1, M3 are nearly coplanar, so we chose to make them out of a single substrate. We did that using the borosilicate technology that had been under development at the Mirror Laboratory at the University of Arizona. This is the first time that that technology has ever been used to produce what is effectively a compound optic, 2 different surfaces in the same substrate. And that's tricky because this process uses a spin casting. So the oven where the glass is melted is rotating at the right angular frequency to give you the near net shape. Obviously, you can do that for one surface. You can't do it for 2 surfaces. So we spun cast this to approximately match the figure for the primary and then had to remove a lot of additional material to make the secondary. In addition, those 2 surfaces had to be concentric to a fraction of a millimeter. So over an 8.4 meter optic, that was a real challenge, and it was a real question whether that would be achievable. But I'm proud to say this is complete now. The top image here shows you the completed mirror being lifted with a vacuum chuck off of its polishing facility at the U of A. This was a somewhat delicate operation, as you can imagine. It's now in storage. The bottom figure shows you the weldment for the mirror cell, which will contain all of the active components, the actuators and the hard points to position that mirror. And the integration of that mirror into its mirror cell is occurring in the remainder of this calendar year and should be complete by January or so. And then we will bring the completed optic in its cell back to the mirror lab at the U of A to interferometrically test the mirror in its cell. The secondary mirror is being fabricated by Harris Corporation. This is a tricky optic as well because it's convex. The substrate is 50 millimeter thick meniscus ULE glass from Corning. This is currently in optical fabrication in its cell as well. The bottom picture shows you the ground optic in its cell. And the integrated optical testing should be completed again by the end of the calendar year before we ship to Chile. So LSST, as I mentioned, will be sited in central Chile. It's on an Aura site, which currently houses the Gemini South telescope, which is an 8-meter telescope, and the SWORD telescope, which is a 4-meter. So this is a well-developed astronomical site, which saved us a lot of money in terms of power, roads, et cetera. A lot of infrastructure was there. The building is being undertaken by a Chilean company called Bisalco Construcciones. That figure at the top is a diagram. It's a rather complex building, as you can see, and a very large building. So you have the telescope mount in the dome on its pier here. There's a very heavy lift elevator that can be used to move the mirrors up and down to a coating facility so they can be recoated over the 10 years. And also the camera, which is also physically very large, so that it can be serviced. And there's a camera clean room in the support part of the building here to service the camera, as well as the control room, et cetera. We're also building an office building in Chile at a compound that Aura runs in La Serena, which is a nearby coastal city. The telescope dome is being developed by a company called European Industrial Engineering in Italy. They have fabricated all of the components, and EIE is now at the site in Chile installing the dome. This is similar to previous domes that this company has made, in particular for the very large telescopes of the European Southern Observatory. But given the large field of view of the LSST camera and the telescope, we had to include a separate light windscreen to suppress stray and scattered light. With a wide field of view, this, as you can imagine, stray and scattered light is an issue, as well as with such a large opening, wind buffeting in the dome. The dome is highly louvered. So current work is focused on the azimuth rail section and the bogey wheel installation on the lower enclosure pier, and that's going on now. The telescope mount assembly is being developed by a consortium of Spanish companies led by Geisa Engineering and Astrofieto. The strong constraint on the mount is that it has to be squat and stiff, because once again, we're moving this telescope around essentially every 30 seconds or so, and typically we're going a few degrees away in the sky. So again, we can't allow for any slew and settle time. It has to be a very stiff structure. This makes it look quite different from some of the comparable aperture telescopes that you may be familiar with. The current state of it is shown in that lower figure. As you can see, the azimuth structure has been built. The azimuth assembly floats on a hydrostatic bearing oil system, and initial system testing will occur in the next few months. Let me turn to the camera. The camera is a very complex beast. This will be the largest digital camera ever fabricated for astronomy. The entrance lens, L1, is 1.6 meters in diameter. The whole camera weighs several tons. It's roughly the size of a small SUV. Various components of it are shown here. There's this structure, L1, L2, which contains the first and second lenses, a shutter, the camera body, a complex filter exchange mechanism that allows us to insert one of the filters into the field of view, a cryostat, which is a vacuum vessel with an entrance lens that forms the third key element in the camera system, L3, and then a utility trunk with the electronics bays and the cooling system. The focal plane runs at essentially minus 100 degrees, which means we have to keep it cool with an active system, and it generates a lot of power because there's a lot of channels of electronics in the system. The biggest constraint is that since we're doing exposures that are essentially 15 seconds in length, we want to read out the camera very quickly to avoid wasting time with the shutter being closed. So the camera array is 3.2 billion pixels, and we read out that entire array in 2 seconds. In order to do that and not generate a lot of read noise in the CCDs and electronics, we had to highly parallelize the system. So the focal plane consists of 189 4K by 4K sensors, each of which is segmented to 16 separate amplifiers. And so we're reading out thousands of electronics. That hasn't been done typically before in an astronomical camera. It looks more like the central detector of a particle physics detector, and so we had to design appropriately for that condition. So this is a schematic of what the focal plane looks like. Each of those blue squares is a 4K by 4K CCD. We group them in units of 3 by 3 onto what we call rafts. So the red squares correspond to individual science rafts. And each of those science rafts has its full processing electronics in the footprint of those 3 by 3 array of sensors. Every one of those rafts is a 12K by 12K camera in its own right, and the output of each raft is a single optical fiber. And then, of course, we have to align all of these structures together. Given that the system is very fast optically, f1.2, the tolerances on the mechanical flatness of the overall array are quite tight, and on the flatness of the individual sensors as well. We had to develop new sensors, new CCD sensors for this project. We've spent a number of years in that development. There are two companies that have made sensors that meet all the requirements. One of them is E2V Corporation in the UK, and the other is the Imaging Technology Laboratory at the University of Arizona. And in fact, we are using both of those sensors, different sensors, to populate the array. So this raft that I told you about is the basic building block of the camera. You can see the 3 by 3 array of CCDs at the top. There are custom electronics boards that do the digitization and the image acquisition. And again, the output of this is an optical fiber. The raft consists of 3 major assemblies: the raft sensor assembly, the raft electronics crate, and the raft electronics board. And all of those are contained within the camera cryostat space. So another big concern we had with this design is contamination. There's a lot of cabling, a lot of electronics in the vacuum, and of course any outgassing and contamination deposition on the CCDs will change the response of the CCDs and create problems for calibration. The science raft tower modules are being constructed at Brookhaven National Laboratory on Long Island, and to date we've made and delivered about 4 or 5 of the 21 that are required for the focal plane. So these are actual Raft modules. The CCDs are facing down in this picture, and the electronics boards are facing up. The camera cryostat is also a fairly complex beast. It has to support both structurally and thermally the full focal plane and provide the contamination control as well. The rafts are mounted kinematically to a CSIC grid, which was manufactured in Germany at a company called ECM Corporation. That grid had to be mechanically precise, and we chose the ceramic, obviously, for its stability. The heat generated by the electronics, and as I mentioned, there are a lot of channels of electronics, has to be carried out, and so we have a complex refrigeration system for that, which uses a mixed refrigerant technology. The focal plane, there's a Cryo Plate, which is controlled at minus 130 degrees C, as well as a cold plate, which is operating at minus 40 degrees C. The cryostat housing is an optic. It's the L3 entrance window, and that has to maintain the vacuum over 10 to the minus 6 torr over a fairly large area. The diameter of that vacuum window is about 65 centimeters or so. So it's fairly thick. And the camera cryostat is being assembled and tested at SLAC National Accelerator Laboratory in California. And so this shows you some real hardware. We've taken delivery of most of the components of the cryostat at this point. The CSIC grid that I mentioned is shown on the left on a coordinate measuring machine, which is checking the tolerances. And there is an early version of the Cryo Plate on the right side with complex tubing that allows the refrigerant to bring the entire structure into thermal equilibrium. The optics for the camera are also fairly challenging. The largest optic, L1, is 1.55 meters in diameter, L2 is 1.1, and L3 is 0.722 meters in diameter. L1 and L2 are mounted together in a common structure, which is shown on the right. This is single assembly. The prime contractor for that work is Ball Aerospace, with major subcontracts at Arizona Optical Systems in Tucson and at Vanguard for the composite structure. L3, as I mentioned, is the entrance window to the cryostat. It's being developed by Thales Seysso in France. The filters are multi-layer dielectric interference coatings deposited on fused silica substrates. The substrates are curved so that the chief ray is normal to the front surface at all points in the field, and the filter coatings will be produced by Materion. So these filter coatings are also challenging because the filters are physically quite large, again about 60 to 70 centimeters in diameter. We need very high uniformity on those filters, and they're on a curved surface. None of that has been done before at this scale. And the development of all of the LSST optics is being led by a team at the Lawrence Livermore National Laboratory. So this shows you the optics in progress, the L2 optic undergoing testing at Arizona Optical Systems, the L1, L2 composite structure that will hold them together, and the L3 flat barrel, which is with its flange that forms the vacuum seal. So let me close with a few slides on the data system. LSST is also challenging in terms of the data system. Over the 10 years, we'll produce something like a few hundred petabytes of data, which of course is more information than everything that's ever been written in any language in human history. I used to think it was a very large database, but it turns out now it's a few percent of all the cell phone pictures taken by everybody in the world. So that data volume is larger, but we're a few percent of it. But I don't think anybody is planning to do organized scientific queries of all the cell phone pictures ever taken by humans. So we have a complex data system that includes getting the data out of Chile to our major computing facility in Illinois at the National Center for Supercomputing Applications. There are two redundant fiber optic links that we've developed. Those are 100 gigabit links for redundancy. There's a base facility in Chile which will do some of the real-time processing, and there's data storage capability on the summit itself. The ultimate LSST deliverable, of course, is these reduced data products. So for that, we have a petascale supercomputing facility at the LSST archive in Illinois. But we also have to develop what we call data access centers so that astronomers and scientists both in the US and elsewhere in the world can actually do something useful with the data. The problem at this scale is not so much storing the data or processing the images. The problem is finding anything in the catalogs. The catalogs are trillions of lines long, and the kinds of scientific investigations people will want to do involve complex queries on those very large catalogs. So this is a rough sort of indication of what kinds of processing we do. There are 3 levels, as we call it. Level 1 is the nightly system, where we process these images very quickly, determine the time domain events. There are about 10 million per night. We also, it turns out the largest component of those time domain events are asteroids. So we need to recognize that changing things in the sky are asteroids and determine their orbits so that we know the next time we see them that they're asteroids. So we have to catalog all the moving objects. There'll be about 6 million bodies in the solar system that are cataloged. Every year we'll do the annual data release. As I mentioned, about 37 billion objects will come from that. 30 trillion force sources will produce deep co-added images. And then a lot of the science that the community will do will involve software that they develop for particular investigations. And we have to be able to facilitate that through an intelligent system that will take user-provided software and make it available to run on the data. The LST data volume is so large that you don't send the data to the user. Basically, they send their jobs to the center. Otherwise, the I/O access times are much larger. And so there'll be custom software and APIs developed to enable those user-developed codes. This is a structural diagram of the data management system, basically 3 layers: an infrastructure layer, a middleware layer, and an applications layer where the science pipelines will run. And physically, these components will span 4 key facilities on 3 continents: the base facility in La Serena, Chile, the Central Archive facility in Illinois, and there'll actually be a satellite data processing center in France at the Computing Center for IN2P3 in Lyon. In order to enable the users to access the data, we'll develop what we call a science platform. This has to be structured to support novice users who want to do relatively simple things, and then increasingly serious users who want to federate rather complex analysis codes with this. And we've built a system that relies on what we call a portal, Jupyter Lab notebooks that take sort of custom Python code and run naturally, and then web-based APIs. Let me just have one slide on education and public outreach. LSST is a marvelous tool for engaging the lay public in the natural science of looking at the universe. As I mentioned, everybody in the world can own a few galaxies, a few stars. We can distribute a galaxy to every school in the world, and the kids in each class can look at that galaxy and see if a supernova went off. And 250,000 times a year, a supernova will have gone off. In most cases, those school children will be the first human eyes to actually look at that image. Of course, we'll detect it automatically, but it offers the possibility for direct engagement with the natural world that we hope will increase participation in sort of STEM education and STEM fields from a much larger segment of society than has been true in the past. We have an extensive education public outreach program. It involves web tools, it involves physical presence in classrooms, in planetaria and science museums, et cetera. And we're engaging in those partnerships now to make that all possible. So let me close just by summarizing. LSST is a highly complex system. It's pushing the state of the art in many technical areas, and essentially in all technical areas. In order to build this, we've assembled an outstanding distributed team to accomplish the work. We decided early on that we were not going to be able to build this project by deciding to put it somewhere and hiring everybody we needed to come to one particular location. So we looked for sources of expertise wherever they lived, and that led us to a very distributed system. We have activity on LSST in Princeton, in Illinois, in Seattle, in the Bay Area in California, in Pasadena, in Tucson, in France, and of course our vendors are located all over as well. The project is on track to achieve first light in 2020 and to formally begin its decade of operations in October of 2022. This will be a world-unique facility that we hope will make fundamental discoveries in a wide range of disparate fields, but even if it does it, it's been a real trip just trying to build the thing. So let me close there. Thank you.